Okay, let's dive into this. Imagine you're trying to study something really fundamental, like an antiproton.
Right.
The place you make them, CERN's Antimatter Factory or AMF, it's also buzzing with electromagnetic noise from all the accelerators.
It's a real challenge. It's a bit like trying to hear a tiny whisper next to a jackhammer.
Exactly. And this noise, it's not just annoying, is it? It actually limits how precisely you can measure things.
It absolutely does. You see, we have this fundamental principle in physics, CPT invariance. It's core to the standard model.
Uh-huh.
It basically says the laws of physics should stay the same if you swap charge, flip coordinates like in a mirror, and reverse time all at once.
And antimatter is key to testing that. Because if matter and antimatter behave even slightly differently,
It'd be huge, a massive discovery. It could mean, rethinking our fundamental theories. We look at things like antiprotonic helium or even whole antihydrogen atoms.
okay, so precision is everything. Which brings us to what we're really digging into today, this pretty amazing achievement.
Yes, the successful transport of protons. Now, protons aren't antiprotons, but moving them like this is a huge step towards being able to move actual antiprotons.
Taking them away from that noisy AMF environment.
Exactly, moving them somewhere much quieter where these super delicate measurements can actually be done properly.
And we're drawing this from a Nature article detailing this experiment using something called base step.
That's right. It's a transportable penning trap system. This successful proton transport, well, it really opens the door to a new level of precision in antimatter research. It overcomes a major bottleneck.
All right, let's get into the weeds a bit. Why exactly is it so hard to do these measurements at the AMF? What's this noise actually doing?
Well, the big culprits are the antiproton decelerator and the synchrotron, essential machines, for making the slow antiprotons we need.
But noisy neighbors, electromagnetically speaking.
Precisely. They cause fluctuations in the magnetic field inside the experimental hall. And these fluctuations, even tiny ones down at the nanotesla level.
Nanotesla. That sounds incredibly small.
It is. But these experiments are incredibly sensitive. They measure things like spin precession, how a particle's spin wobbles, and cyclotron frequency, how it orbits in the magnetic field. Both depend directly on the magnetic field strength.
Ah, so if the field is wobbling, your measurement wobbles too. It's like trying to weigh something on a shaking scale.
Exactly that. The BASE experiment, for instance, they got the world's best measurement of the proton-antiproton charge-to-mass ratio comparison,
Uh-huh.
but they were hitting a wall because of these magnetic field jitters. The goal now is to get the uncertainty from these fluctuations below 1 nanotesla. It's a very demanding target.
Wow. Okay, so if the environment's the issue, you move the experiment.
Yeah.
But that sounds complicated. How do you move a particle trap? That's where base step comes in, right?
Yes, base step. It's a really clever bit of kit. It's basically a self-contained transportable pinning trap.
Self-contained how?
Well, key things are it's superconducting. Once you cool its magnet way down, it can run for hours without external power to the magnet itself. It's autonomous, runs on batteries and its own cooling for a while. And crucially, it's got an open design so you can get particles in and out.
So, like a high-tech thermos for charged particles.
Yeah,
Keeps them trapped and isolated while you move them.
that's a good way to think about it, yeah. Being able to shuttle antiprotons to super quiet labs, it's been a dream for a long time in this field. Base step is a huge leap towards making that real.
Okay, fantastic piece of tech. So the big test, what did they actually do?
They ran this crucial proof of concept experiment. They successfully transported a small cloud, about 100 protons.
Protons, not antiprotons yet, but the principle's the same.
Exactly. If you can do it with protons, you're well on your way to doing it with antiprotons, which are much harder to come by. So they loaded these protons into base step right there in the AMF.
And took them for a drive.
Pretty much. They planned this route very carefully across CERN's Myron site. It was 3.72 kilometers long.
Wow. How did they move it?
It involved overhead cranes inside the building, then carefully loading the whole 800-plus kilogram system onto a truck.
On a truck. That sounds bumpy for sensitive physics.
It definitely could be. They reached speeds up to about 42 kilometers per hour on the truck.
And how did the system handle vibrations, the movement?
That's where the autonomous part is so vital. The superconducting magnet just kept running, powered by internal batteries, cooled by its own liquid helium supply. It ran autonomously for 4 hours straight, no external hookups needed.
Impressive. But surely there were challenges. Temperature. maybe.
Oh, absolutely. Disconnecting the main cooler, the pulse tube cooler they use when it's stationary, and then reconnecting it later, that caused temporary temperature spikes in the system.
That sounds bad for a superconductor. Didn't it quench? Lose its superconductivity?
Well, they were ready for that. They designed countermeasures like a heat exchanger on the helium exhaust, and they could carefully tune internal heaters. So they saw spikes, yes, up to around 7 Kelvin. But critically, they managed to keep it cold enough. The persistent current in the superconducting wire never broke. The magnet stayed superconducting throughout the whole transport.
That's amazing engineering.
Yeah.
What about the protons inside? Did they get jostled around? Did they lose any?
They watched them constantly using something called image current detection, basically listening for the tiny electrical signals the oscillating protons make.
Uh-huh.
They used an FFT spectrum analyzer to monitor the frequencies. Now, during the truck ride, they did see some temporary frequency shifts, probably tiny grounding changes or wires moving slightly.
But temporary.
Yes, transient effects. The really key result was when they checked afterwards, the transport was essentially lossless within their ability to measure anyway.
Meaning?
Meaning the number of protons they counted before, around 105, was consistent with the number after, around 104. The small difference is within the measurement uncertainty. And importantly, the protons didn't seem to gain any unwanted energy in their sideways motion, which could have kicked them out of the trap.
So they put roughly 100 protons in a box, drove them nearly 4 kilometers across CERN, and basically got all of them out at the other end.
That's the gist of it, yes. A remarkable bit of precise handling.
Let's talk a bit more about the tech itself, base step. What's actually inside?
Okay, so the heart is the penning trap. It uses a strong, very uniform magnetic field, usually from the superconducting magnet, to confine the particles radially, sort of sideways.
Right.
And then it uses an electric field, a special shape called a quadrupole potential, to trap them along the direction of the magnetic field. This potential is created by carefully shaped metal tubes, gold-plated electrodes.
So magnetic field holds them in, electric field holds them along the axis.
You got it. And the protons oscillate back and forth along that axis. In this setup, it was at a frequency of about 383 kilohertz.
And they detect that oscillation.
Yes, with that superconducting image current detection system, it's very sensitive and doesn't really disturb the protons much.
And all this fits into that transport frame, the 850 kilo thing.
Yeah, the frame holds the track system itself, plus all the support gear for autonomous operation. The UPS batteries, control computer, frequency generators, voltage supplies, amplifiers, heaters, everything needed to keep it running on its own.
Sounds like a portable lab bench. How did they keep it cold during the move, specifically?
So when it's parked in the lab, they use a pulse tube cooler, like a cryo cooler. But for transport, it relies entirely on an internal tank of liquid helium, about 30 liters capacity.
And it used about half of that for the 3-hour trip.
Roughly, yes. About 13.5 liters boiled off during the 3 hours and 21 minutes of the actual transport phase. Oh, and another neat bit of engineering to save space and power, they developed a custom, really compact FFT analyzer using just a standard sound card. Pretty clever.
Very clever. Okay, so protons move successfully. Proof of principle achieved. What does this mean for the future? Where does this lead?
Well, the immediate big step is applying this to antiprotons, moving actual antiprotons out of the AMF to these dedicated offline labs.
Labs designed to be ultra-quiet.
Exactly. Much lower magnetic noise, better temperature stability, you name it. There's already a plan to deliver antiprotons to a new experiment being built at Heinrich Heine University in Düsseldorf, Germany.
And a goal there.
The goal is CPT tests comparing protons and antiprotons, aiming for at least 100 times better precision than what's possible right now.
100 times. That's a game changer, isn't it?
It really is. A jump like that could potentially reveal tiny differences between matter and antimatter that we just haven't been able to see before.
And could this lead to, like, multiple labs doing this kind of work?
Potentially, yes. Looking further out, you can imagine parallel measurements happening in several specialized labs across the world. Think about the cross-checks, the different systematic effects you could study. It really boosts the reliability and depth of the research.
Sort of distributing the high-precision work. Are there other developments alongside this?
There are. People are also working on transportable traps that use permanent magnets instead of superconductors.
What's the advantage there?
They could be cheaper, maybe less complex to operate, potentially less risky than handling large superconducting magnets during transport. They might also make it easier to inject the particles into the trap initially. It's an alternative approach being explored.
Interesting. And is it just antiprotons this could work for? Or other antimatter too?
Good question. The technology could potentially be adapted for other charged antimatter systems too, if and when we can make them efficiently. Things like the antihydrogen ion that's an antiproton with two positrons, or maybe even the antihydrogen molecular ion.
Wow, so moving a whole antimatter molecules around eventually.
It's a possibility down the road. But the core benefit, the really big deal right now, is ensuring that future experiments aren't fundamentally limited by the noise where the antimatter is produced. You decouple production from high precision measurement.
Right. Get away from the noisy factory floor.
Exactly. And they even showed they could extract some of the transported protons, simulating how you'd pass the antiprotons to the receiving experiment. They pointed out that the number of protons they moved in this test run, that'd be enough antiprotons to keep an experiment like BASE running for several years.
It really puts it in perspective. It's not just a few particles for a quick look. It's a viable supply for long-term, high-precision work. This really does feel like a massive step.
It absolutely is a major advance for antimatter research and really for fundamental physics as a whole. We're trying to understand the basic symmetries of nature.
So it really makes you think, doesn't it? What happens next when we can study antimatter with this incredible precision routinely in these quiet labs?
Mm.
What might we find?
Mm.
Could this be how we finally get clues about dark matter or figure out why there's so much more matter than antimatter in the universe?
Yeah.
Taking something as exotic as antimatter and being able to bottle it up and move it around, it feels like science fiction becoming reality.
It's an incredibly exciting time for the field. The potential for discovery is, well, it's immense.